In this video, I will talk about the concept of efficiency in an ideal gas engine. And this symbol, this is what we use for efficiency of an ideal gas engine. And when I say an engine, I mean an ideal gas cycle. If you look at the PV diagram, if the ideal gas is completing a cycle, that can represent an ideal gas engine. Now, efficiency of an ideal gas engine can be calculated as a fraction. The fraction has the numerator as what you get, what did the engine do for you, over what you paid for. So in the denominator, you have to include how much energy you provided to the engine to do what you wanted it to do. Now, typically, when you have an engine, an ideal gas engine working for you, then the numerator will be the work that the engine did and when I say, keep in mind, when I say engine, well, I mean really this means the ideal gas. Okay, so it's the ideal gas that is doing the work. It's the same thing. So in the numerator, you will have the work that your ideal gas engine did. And in the denominator, when you have an engine working, what you need to do, you need to provide some thermal energy to your engine. You need to use some kind of flame. You need to burn some fuel to raise the temperature of the surroundings so that you can have some thermal energy transferred to the engine. Now, thermal energy transfer is heat. So what we pay for is heat. The heat from the hot surroundings that get transferred to the engine. So what I will show you in the next few minutes is how you can calculate efficiency for the example that I went over in my previous videos. All right. Now I summarized here the Q and the W, heat and work, for the three processes of the ideal gas engine that I have analyzed so far. Now it is important to remember that all of these, okay, I got all of these based on what I used in the energy conservation principle. So this Q and W is about what the surroundings did. What the surrounding did on the system, from the surrounding on the system. The system is the ideal gas engine. Okay, the system is the engine. Now, I want to remind you though, efficiency is defined as what we got over what we paid for. Now, what do we get from the engine? We get the work, the useful work that the engine did for us. Now, the work that the engine did is the opposite from the work that the surroundings did on the system. Okay, let me do a calculation. So what I'm gonna do here, I'm gonna find the net work, the total work that the surroundings did on the system. I have minus this plus that plus 0. So the net work minus 1600 joules. This is how much work the surroundings did on the system. Okay, the work that the surroundings surroundings did on the engine, on the system. Now, to find efficiency though, I don't need to know how much work the surroundings did on the engine. I need to know how much work the engine did. And to find that, I need to include a minus sign. So the work that the engine did is 1,600 joules. This is the work that the engine did on the surroundings. Now, this is what I got from the energy conservation principle, but this is what I need to use when I calculate efficiency. So, here is efficiency. How much work, what did I get from the engine? The engine did work equal to 1,600 joules to the surroundings. Now, I also need to divide it with something, and that something is what I paid. What did I give to the engine in order to get this amount of work from the engine? What we pay to an engine, as I mentioned before, is the heat that we provide to the engine so that we can work. And we provide heat by burning fuel or by maintaining a flame or something of that kind. Now, when I have my system and the flame next to it or the burning fuel next to it, then Q will be a positive number. Q is what I transfer from the heat, from the flame, from the burning fuel to the system. In that case, Q will be a positive number. Now, if you see here, I have from the process 1 to 2, Q is positive, 2 to 3, Q is negative, and from 3 to 1, Q is positive. Now, what I did, I had a flame, I had some burning fuel next to the engine to provide some heat for processes 1 to 2 and 3 to 1. So the heat provided to the engine using some sort of flame or fuel, okay, whatever you want to call it. This was done here and it was done here. Now you'll say, well, what happened in process 2 to 3? From process 2 to 3, it was actually the engine that gave some heat to the surroundings. And that means I don't need to have, when the ideal gas goes from state 2 to state 3, I don't need to have some burning fuel next to it. Instead, what I need to do is have some kind of cool water, if you want, so that that cool water will absorb that much energy from the engine. So when you have an engine working, you need to have both a way to provide heat, but also some way of absorbing heat from the ideal gas engine. Now, what did I pay? What did I give to the engine to do its work? Well, I gave it this much from process 1 to 2, and I also gave it this much from process 3 to 1. So what I paid in total is the 6,400 plus the 6,800, and all of these are joules, of course, and this will determine the efficiency, and this will give me 0.12 or an efficiency of 12%. So my ideal gas engine has an efficiency of 12%. It is, you may think, well, that's very low. It is low, but that's not surprising. So this was an example of how you can calculate efficiency. Remember, it's calculated as what you got, the work that your engine did over what you paid for, how much heat you gave to the ideal gas engine by burning some fuel or maintaining some sort of flame.